In this lecture, we're going to look at some issues surrounding designing your own data types. And in particular, we'll talk a little bit in the beginning about object-oriented programming and what it is and how it differs from some of the other programming paradigms. We'll talk about data encapsulation. So this is an important concept and consideration. When you start designing your own custom data types, it's something you want to think about. We'll talk about how you do that with access modifiers. We'll also look at immutability, which is designing classes, designing data types that can't be changed, and it has some practical consequences for some of the objects you'll commonly use, like, for example, the string object. And finally, we'll talk about a somewhat the somewhat hairy business of checking for equality. You might think it's quite simple. Is this variable equal to another variable? But once we start dealing with more complex data types, like things you build yourself, or built-in data types like color or string, then actually equality is not as simple as you might think, and it can often get you into some trouble. In the olden days, people used to do more procedural oriented programming. In this style of programming, it's very much you tell the computer what to do, you tell it to do this, then you tell it to do that, and then you tell it to do the other thing. And that's the style. You just write a sequence of commands that achieve some particular objective. In the object-oriented philosophy, we see software more as a simulation of the real world. We're trying to approximate maybe some natural process or something like that in our software, and as far as it's possible, we try and maybe we model the actual things. If we're implementing a software program that simulates the motion of the planets around the sun, we might actually design data types for the planets and so on. If we can simulate and create data types that map to the real world, it might make our software design easier. This whole idea of object-oriented programming surrounds data types. You can't have object-oriented programming without designing your own data types, and part of that process is first to identify what are sensible data types. What do I need? I've got this simulation of the planets around the sun. Does it make sense to have a data type for a planet? And is that different from the data type for the sun? Or maybe there's a spaceship or an asteroid, or various things like that. There might be needs for different kinds of data types, and maybe each of those data types needs some support data types. Doing object-oriented programming is first about doing that design. So before I start writing a program, I might spend a lot of time thinking about, well, what objects make sense for this particular problem I'm working on. Once you decide the set of data types you need to develop, you have to make decisions about each of those data types, like what is its persistent state, what do the objects know about themselves, what are the set of values associated with a particular data type, and then also what behavior, what do you want the object to be able to do, what can you ask it to do, calculate, show, draw, and so on. And this is not my idea, obviously. It was this guy's idea, Alan Kay. And Smalltalk was the very first object-oriented programming language, and among his other achievements, he developed the first portable computer, so kind of a predecessor to modern things like the the iPad. And there's a photo of the Dynabook there. 1968. That's a long time ago. That's a long time before the iPad. And some of his ideas led to a lot of things you now take for granted, like the laptop and the GUI environment and object-oriented programming. And there are some quotes showing, sort of his visionary nature. And there he is with his medal, his Turing Award. So a Turing Award is essentially the Nobel Prize for computer scientists. A big issue when you design your own data types is data encapsulation. And just as a reminder, right, when we talk about data types, we're talking about something that has a set of values and operations on those values. And here, just some examples. And normally, remember, like int is actually a primitive type, but it still has a set of values and operations on the values. When we're designing our own data types, we're designing things like charge and picture and an enemy or a player class. And one of the issues is, well, how do we represent that set of values? And a principle we'll normally adhere to when we're designing a data type is data encapsulation. Whatever those set of values are inside of my player class, I don't want everybody to be able to muck with it. We want to hide that internal representation inside the data type, and this provides some advantages as far as maintainability of code and preventing other people from having to know that. If you expose these internal details of your data type, then anybody can see them and use them, and then you're no longer free to change them. So one big advantage of data encapsulation is I can represent the set of values that the player knows about in any way I please, and I'm free to change it if I've done my data encapsulation properly. We're going to separate, and here's some terminology, right? A class is the blueprint for an object, and it also contains, in that class file, in that .java file, is all the code for all the operations. So all the code for all the methods, the things the object can do are in there. The client, however, whenever I talk about a client, I'm not talking about this class file that implements, for example, the player class. A client might be the particular game program that's using the player object. It's the client. And clients use data types as a black box. They only know how to call methods and ask the object to perform actions. They don't know and don't need to know necessarily how the class actually implements those things. And that's all defined by this API, the application programming interface. This is the contract between the client and the class. If I'm a client, if I know the API, I call those methods in the API, and I know the people that develop the class hopefully aren't going to change that API, and normally you won't. And the main advantage is it provides a simple interface point between these different bits of code. So if I'm a client code, I can call many different classes. I may have lots of different data types I depend on, but I don't want to know every line of code in 100 different data types. All I need to know is the API, or the part of the API that does the parts I need to get my job done. And here's some intuition about that. You can think of the client as somebody on their recliner they're sitting down on their recliner, they want to watch some TV. Their API, all right, they're on the recliner, right? They can't go up and do anything with the actual TV itself, but they have an API, and what they can do with that TV is defined by what buttons they have on the remote control. They can adjust the volume, change the channel, and so on. A particular implementation of a TV is shown here. So here's an old Sony Wega. I used to have one like this, and I can confirm it does weigh about 241 pounds. They don't make them this solid anymore. And it did the job. It had a very nice picture. As the client of that, though, I just need to know how to use the remote control. I don't particularly care that it's a 241-pound TV or exactly how this guy has got an electron gun and he's shooting things at the screen. I don't really need to know about those details. All I want to see is my picture and flip on Wheel of Fortune or whatever it is I want to watch. The idea of the API and the data encapsulation is then later in life I can upgrade to a nice new Samsung, this is a plasma display, I guess, and it's no longer 241 pounds, it's 4 inches deep. I can put it in easily, I can hang it on the wall if I want, and it still produces a picture. I can still watch Wheel of Fortune, and I still use it with the same remote control. It's just the implementation has changed. All right, we've got a better implementation. It doesn't weigh 241 pounds. The picture is probably better than that old cathode ray tube. But I haven't broken my remote control. This is kind of, your client uses the API, and as long as I haven't changed the API when I implement my new TV, I haven't changed what it means for TV to be TV. If I decided TV no longer has channels, then I've broken the API. But as long as I haven't changed that API, the client can continue to use the implementation without knowing exactly how it's done. So that's the idea. And when you don't do this, you get yourself into trouble. Perhaps you've heard of the Y2K problem, and this all stems from computer scientists failing to encapsulate their data. And way back when they're developing software, they thought, well, it's never, this software will surely be replaced by the time the year rolls around to 2000. I developed this software in 1972. It's not going to be around in 2000, surely. Well, turned out a lot of software was still around, and people were writing code that directly accessed these, the internal representation in the software of that year. There was no clean API. There's no clean point you could change. In theory, it's a very trivial change, and if you had all code going through a single point asking please get me the year, you could change that data representation of the year to support years past 1999, and then all the code would just easily work. But because all the code was going directly at the internal representation, you had to find all the locations where that was happening, and that is tedious and time consuming and error prone. And you might be interested to learn there's also, same thing, computers often count the number of seconds since 1970, and and that's going to cause a problem, at least for 32-bit integers, around 2038, so look out for that. How do we encapsulate our data? Well, in Java we have a variety of access modifiers, and these are things we put on the front of instance variables and also on the in front of methods as well. To encapsulate the state, the set of values, we're going to put them on the instance variables, and there are three choices. The actual keywords are the first three: public, private, and protected. Public means what it says. Everybody can see it, everybody can use it. And in general, we won't use this for instance variables unless in very specific circumstances, if it's say just a constant value like the speed of light, we might make that public. Or the color red in standard draw, we might make that public. But things that represent the internal state of your data type should not be public. They should usually be private. Okay, and eventually eventually you'll learn about things like inheritance, in which case you might use the protected access modifier. But for now, your instance variables typically should always be private. All right, and if you don't use one of these three, all right, if you don't declare one of these things, what you're going to get is default, and default is visible to everybody in what's called a package. And normally this isn't what we want either. This kind of makes it semi-public, and it's easy to violate data encapsulation. In your assignments, we expect your instance variables normally to be private unless you've got a good reason. So don't forget to put the private on there and end up with a default package access modifier. Methods that are part of your API are declared public. Otherwise, no one can use them. If you have methods in your class that are just kind of helper methods for other things in your class, they're just kind of utility methods that are only used internally, and maybe these private methods are really intimately related to how your representation of your data type. It's okay to make those private. When you make a method private, only people inside instance methods of the class can access them. Here's a concrete example. We've got a person class, and let's say we've evolved our thinking. Originally we had a person class, and it stored a name and a score of some sort, and we had various methods that could access things like toString just returned the name. At some point we decided actually what we really should do is have a first name and a last name and keep them separate. We want to have two instance variables, one called first and one called last, and we'll still have our score instance variable. And now our toString method has become, a little more complicated because now we have to, concatenate the first name plus a space and the last name and then return it. Alright, that's all well and good, and this is an example of good data encapsulation. So notice the private instant variables we've got on the front of our, in front of the data type. So these access modifiers always go before the type. So we've got access modifier, data type name, variable name, and then an optional assignment. And here I'm assigning this defaults to the blank string, and then it defaults to 0.0. Here's that same thing not correctly data encapsulated, and I've changed these things to be public, and now everybody in the world can access these by just using dot notation. Everybody in the world can access first or last or score, and they don't need to go via the toString method to, for example, print out the name. And what we see here is a broken client. By making this change, how we represent the name is really internal state to the person class, and our clients shouldn't really have to care how we did it, but because we expose those details by using the public access modifier, we've broken them, and now this code won't work. And I've got this example, here's an example of the good class. So everything's private, and we've got a client, and the client can only access things via methods. So the basic principle is you can't get to score or first or last from this client class. It's not allowed. I create the person object P. All right, I can try and do something like this. All right, so let's say, for example, for simplicity, let's get rid of that. Let's just instead of calling p.getScore, let's just try and go p.score. This will not be allowed, and Eclipse is going to say the field person.score is not visible. We either have to change the access modifier, which would be naughty, or go via a accessor method. And what I did to this person class is I added a very simple method. All right, you have to type a little bit. It's not very complicated. It's not rocket science. I made a specific method, and all it does is return that instance variable. I provide access. People can call, obtain the score, but they must do it via my method. And the key part of this kind of design is I'm free to change this to some other representation of a score. Okay, and everybody else, I know all my clients have to come through this method, and I can change this method code in one place, and then all my clients will continue to work. Whereas here is a bad example of data encapsulation. And notice I didn't put the public here, I just did the common mistake of not putting any access modifier. So I've got package level default access modifier. And this is great. Here's the original version. It has a name, this is a single instance variable, and a score. And people can assign it with the constructor and obtain it here. And here is a client, and at this level, okay, it works fine. All right, there's no problem with this currently. This guy can get the p.name and p.score because I haven't put that private instance variable access modifier in here. The trouble is, if I decide to change this name, even if I just do this, or if I decide I want to have the two instance variables like before, all right, and let's just for speed, here's the code that splits. This code here splits the string into the first name and the last name. I can copy that code, and I can copy the code to toString. So I'm essentially just paralleling the change I made to the person class there. As far as I'm concerned, as the designer of this data type, I've handled it. I've made this change. I've made a more complicated constructor that splits things up. I've made a more complicated toString that does that. Oh, and I think I forgot I need to add, I should have, oh no, I'm not actually using that in the client. But now I've broken, all right. First of all, I've broken it. There's no name member variable anymore. And I've broken the clients, and this might not be me. So it'd be one thing if I was the one controlling this code, but if I design this person class and 100 people in my company are using it, and I've now broken all their client programs, and then people are angry and upset with me. That's the idea of data encapsulation. It doesn't come completely for free. As you saw, in order to encapsulate that data using the private access modifier, I had to add some methods like that get score method, and these are called getter methods or accessor methods. And if I allow people to change something, so this is a getter and a setter for position X in some kind of class. If people can get it, I need to provide a getter, and if people can change it, I need a setter. And they're usually one-line little methods. Not a lot of typing, but you know, some people get a little grumpy to have to type this. But I would advise you not to worry so much. I mean, this is easy to do. You're not going to screw it up. It's a pretty simple, well, you know, probably not going to screw it up. You know, it's a pretty simple method, and what you've done is bottleneck. Everybody that wants to ever change this position X has to come via this method, and that's a huge advantage for, you know, not only data encapsulation, also if something's going wrong and you need to debug your program, you have a nice location. If I want to put some debug statements to print something out, I want to know when anybody ever changes the X position, I can put a system.out.println right here in my setter. And because, you know, that pos X is private, I know no one else can get to it, and they have to come via this method, so they have to go through my debug print statement, and that can be a huge boon for your productivity when you're trying to fix problems in your programs. Next topic is immutability, and an immutable data type is one that you can construct, but then you're not allowed to change it. And we've seen both mutable and immutable objects in the course so far. An example of a mutable one was the picture class, and so the picture was a 2D array of color objects. And remember, you could get color objects, but you could also set them. That's mutating it. That's changing it. You create one picture object. It starts out as a completely blank picture, and then you go through, scan through those, and set the different values, or take the original image and then change all the pixels to grayscale, or invert them, or scale them, or do something like that. It's a changeable object. You create one object, and then you can muck with it and change it around. Same thing with arrays. Arrays are actually, data types in Java as well. You can change arrays. But other things we've seen, like the charged particle class, you create a charged particle at a certain location with a certain charge, and that's it. It doesn't provide any functionality for moving that charged particle around. Same with color. You create a color object with a certain RGB triple, and it's always going to be that color. All right. Any of the methods like that make any changes don't actually change that object. They return a new object. They return a new color object. You can ask a color object to brighten itself, but it actually just returns a new object that's brighter and leaves the original one unchanged. And most importantly, string is like this, and this has some important consequences as a programmer. So it's important you understand the string data type in Java is immutable. And why would you build something like this? Well, it helps avoid some classes of bugs, makes it easier for you to debug your program, and scopes, what kind of code can actually change the values. And you can pass it around. If I pass a string into something, I know no one's going to change it before I get it back. And it has advantages like that, but it also has disadvantages, is that you may want to just make a simple change to a string, but you can't do that. You have to create an entire new string. You can't just change it. And I've got a practical example to show you what I mean with strings. Here is a string program you might think works. I create a string, put in hello world, print it out. I operate on that string object S. I say, string object, make yourself uppercase, and then I print it out. You might expect this to work, but you'd be wrong. This does not work. And it's not a compile error, it's not a warning or anything like that. It's just a bug. This string data type is immutable in Java. You're not allowed, once you construct this and this string s has hello world, it always has hello world and nothing else. What toUpperCase actually does is takes that original hello world, converts it all to uppercase, and then returns it back. And if you want this code to work, you need to do something like this. S equals S. We've created a new string here that's the uppercase version, and then I've overwritten it and put it, I've assigned the reference variable S to be that new overwritten one, and I've lost track of this old one that had a mixed case. Important you understand that with strings. When you're trying to do immutability, or if you've got other things like constants, a handy thing to know is there's also a final access modifier. You can declare instance variables final, you can declare local variables final, and what you're doing is telling the world that this variable can only have one value. Once the value is set, it's final. No one can change it ever again. And this can help you prevent bugs. If you've got something and you don't expect it to ever change, like you've got a constant that's the speed of light, you don't want to accidentally change that in your program. You can put final on it and it will prevent a primitive value like that from changing its value. And it can help enforce immutability. It turns out it's not completely foolproof, but we'll often use it. You'll see me use it if I've got a constant value or something. I'll declare it final, and it just makes it easier to read as well, because as a reader of the code, once you see something declared as final, you can think mentally, okay, now I don't have to have the hypothesis that this variable could change its value. It's declared final. I know the language is going to enforce that, and I have confidence that it can't be changed. And I can show you you don't have to use final to make something immutable. Here's the charge class, and they, arguably we should have probably put final before both of these. All right, if you have an instance variable that's final, you're allowed to assign it in the constructor, but once it's been assigned, it's permanent. But it's still an immutable class even without the final keyword hint, because we construct the charge object and we set the Rx and the Ry in the charge, but we provide no functionality to change that. We can compute potentials at other locations, we can print it out, but there's no set X or set Y or set charge. We're not allowed to move the charge particle or anything like that. It's an immutable object. If I want to move C1 to a different location, I've got to create a whole new charge particle. All right, it's an immutable class, immutable data type. Final topic for today, equality. Comparing things and seeing if they're equal or not equal. All right, we're going to use equals equals or not equals. But for some data types this works and some data types it doesn't. So the take-home message I want you to get through your head is, whenever you try and test something for equality in a programming language, you should stop and think, is this doing what I think it's doing? Because it's not always the case it is. It depends on the data type. In Java, it depends on the data type. Other languages, it might work on different data types. You have to be very careful with equals equals and not equals. Depends on your data type. In this case, in integer land, if we're using an int variable, there is no issue. All right, integers are exactly represented. They have an identical bit pattern in memory. If I assign a equal to 5, I can test it. Is it equal 5? That will return true, and then I'll print this out. I can decrement it, and it will hit exactly 0. It's always safe to compare integer primitives with equals equals or not equals. No surprises there. Here's where we get into some trouble. Floating point, and by floating point I mean the double primitive or the float primitive. You can't represent all floating point numbers exactly. All right, there's only so many bits of memory. A double is only so much space in your computer's memory, and you can't represent the infinite number of floating point values. Remember, you could just have, pi or something, a non-repeating, non-terminating decimal or something like that, and you don't have an infinite amount of memory. And they have to do the best they can, and it has surprising consequences, like this program. If you look through this program, I'm assigning A to be 0.1, 0.1, 0.1, or well, that's obviously 0.3. B is obviously 0.2, and C is obviously 0.0. And clearly this should be true, and this should be true, and this should be true. All right. But obviously I'm not showing you this because these things all work as you might expect. All right. Our hypothesis is all print out, right? But which one doesn't? A doesn't. Well, what the heck? Why would it doesn't make any sense, right? This one didn't print out, but then this one did. All right, and then this one did. What is going on? Well, the basic rule is, as soon as you're using a floating point value, you need to be very, very careful and think it through before you use equals equals. If you've done any kind of calculation, and we've calculated a value, we've added some things together, and now we're comparing to see, is A equal to 0.3? And the trouble is 0.1 is only approximation, and 0.1 is only approximation, 0.1 is only approximation. They add together, and this is only an approximation of A. And it turns out the bit pattern doesn't come out exactly equal. This calculation and the literal value 0.3 are slightly different, and slightly different does not equal return true. All right, and I think we can actually let's try and run it in the debugger here. All right, we're running double trouble, so we can see here. You can already see the problem, right? A is in the debugger output here. It's almost 0.3, but it's 0.3004. All right, we're close, but no cigar. And if we step over, we see we skipped that line because this thing is actually equal to 0.3, with no 4 on the end. All right, they had to approximate these floating point values, and as a result, I like to say the road to debugging hell is paved with the bodies of programmers that compare doubles with equals equals. All right, there are things you can get away with, and for example, if you've assigned something to 0.0, you can then come back. If you haven't done any calculation, I mean any calculation whatsoever, if you haven't calculated with C, it's safe to compare it equals 0, 0. But as soon as you do any kind of math with it, use it at your own peril, and you can predict what the result is going to be if you understand the representation, the IEEE 754 specification, but you don't really want to read that IEEE spec in order to know how your programs work. So be careful. Here's how you can do it properly. If I want to just see, I have to define what I mean by close, and here I've defined close being, we're going to call it equal to 0.3 if I'm within some epsilon, some small epsilon, and I've just decided I want 1 times 10 to the 1 times 10 to the negative 9. I've declared a constant, so all uppercase. Use the final keyword here, and I take the absolute value of the variable and the value I want to compare. Instead of A equals 0.3, I take the absolute value and make sure it's less than that epsilon, and now we get the expected behavior. If you need to compare equality with doubles, you're going to want to look for some kind of solution like this. Reference variables, also trouble. Using equals equals and reference variables, like our example ball object, is also a bad idea. What we're doing is comparing the references, the remote controls that actually represent what's stored. B, the variable B is just a remote control that controls the ball object, and B2 is another remote control. And these are just the bit patterns or memory addresses, and we're not actually comparing. What you might expect this code to do is compare this ball's at 0.0, this ball's at 0.0, and this, they're both same radius, so yeah, they should be equal. All right, but this program, if we run it, and here it is. If we were to run this program, only the second one prints out. All right. When we construct two different ball objects, I've got two different remote controls. They point to two different ball objects. They just happen to be ball objects that have the same initial configuration, but they're not the same remote control. What I've done on line 11 is assign B equal to B2's remote control, and those remote controls have the same bit pattern, and thus this is true. But almost never what you want. All right. If you've got a reference variable and you're using equals equals, you probably shouldn't be. All right, in most cases. How do we do this properly then, you might ask? Well, I'll show you in the code here. I've added a method to the ball object, and many reference data types have an equals method. Now, this is just by convention. People call it equals. It returns a Boolean, and it takes an object of the same type. Then my job is to define what I mean by equals, and what I decided as the builder of the ball data type was that I consider them equal if their x's are within some epsilon, the y's are within some epsilons, and the radius are within some epsilon. That's what I consider equal. That's up to me as the designer of the data type. Right? Notice I've ignored color, so this means two balls are equal even though one's red and one's blue. All right, is that correct? I don't know. That's up to me, and I decided that was the way I wanted to do it. So, and if we look at here, the difference is just I'm calling b dot equals in the other guy. So it's not as simple as doing b equals equals b2, but this will actually produce the desired behavior, or in a world where I consider them equal as long as the location and radius are the same, then that's the correct behavior. And this diagram just explains the thing I just talked you through with remote controls, right? B and B2 were separate remote controls, and what I've done here is actually B and B2 are actually really the same remote control here. They're both well, they're not the same remote control, but they're both pointing to the same object. So their remote control is programmed to point to the same object in memory, so therefore they're equal. Yeah. And yeah, so you implement an equals method. That's what I showed you in Eclipse. String variables, also dangerous land, and a very, 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 very common thing I see beginning Java programmers do. You really want to do this. You really want to compare these things. And I should put this code block in red, I think. But you really want to compare strings with equals equals. Well, you want to, but you shouldn't. All right. And in some languages you'll get away with this. In Java you will not. All right. Strings are reference variables, just like a ball object is a reference variable, and you should not compare them with equals equals. This is a bit of an amazing example, right? We've got A being hello, B being hello, C being hell plus O, D being hell, and then on the next line I add O. All right. You might think, well, these are all equal to each other. They all end up with the string hello, and certainly even if there's something weird going on, right? C and D, those should, this is really the same thing. I'm taking hell and I'm appending O, and here I'm taking hell and I'm appending O. You would think that would be the case, but here's string trouble, and no compile errors, everybody's happy, and oh, okay, is A equal B? Yeah, okay. So you're thinking, okay, I can compare strings with equals equals. Does B equal C? Oh yeah, that works too, and so these three are all the same. Great, equals equals totally works. And then I go and do something like this, and now C doesn't equal D. What the heck is up with that? Like, why is this different than, why is doing it like line 7 different from doing it in line 8 or 9? And there are reasons, this is the case because of how Java allocates strings and so on. But the bottom line is none of these lines should ever have been written. All right, never, almost never ever, unless you really know what you're doing, use equals equals in strings in Java. Okay, always always trouble. How should you do it? Look up in your handy string Java docs, look up the API to string, and what will we notice? There's a equals method, just like I showed you for the ball object. You can see if two strings are equal. This is the correct code. Whenever you're comparing strings, use dot equals. All right, always, always. And this code will behave regardless of how I did this. In my world, strings are the same if they all have the same letters, including case. Okay, so this equals method is with case, and if you don't want that, call equals ignore case. All right, but if you call equals, it's got to be exactly the same, including white space and case, and that's how you should compare strings. To summarize, we went and reviewed some things about object-oriented programming, and we also discussed the important topic of data encapsulation as a a beginning class designer, and you'll be designing some of your own classes and upcoming assignments. You should practice the principle of data encapsulation. Hide that internal state. Don't let other people muck with it. You protect yourself by using the private access modifier in your instance variables. You can make your data types immutable if necessary, and most importantly, you should understand data types like string in Java are immutable, and you can't ever change them. So all you can do is create a new one that's some modification of some original string object. And then another very important topic is equality. You might think it's trivial, but it's not. You need to be careful, especially when you are equating floating point values, reference variables, or string variables. Always think it through when you use equals, equals, or not equals, and make sure you're doing the right thing.